Awesome, thanks, Suki. So yeah, like Suki mentioned, my name is Carson Pruitt. So my background is in GIS programming, automating different GIS processes for different, few different federal agencies. My education trained in geography, focused towards fluvial geomorphology, and also a little bit of biology for that as well. But so myself and Fernando, Aristizabal, and Katherine Powell are going to give you guys kind of a joint presentation today. So I'm going to let Fernando and Katherine introduce themselves before we jump in. Fernando?
Yes, Carson, thank you. So my name is Fernando Aristizabal. That was very good, Carson, by the way. I'm a senior research scientist. I work for Linker. I've been working with the Water Center full-time since the summer of 2019, so almost 4 years. And before that, I participated in the Summer Institute that's collaborated with Quasi on for 2 years. So I've been kind of around this effort for quite some time. And my primary role there is to do some of the R&D work concerning the flood inundation mapping capabilities that we're going to go over with today.
Thanks. And Katherine, do you mind introducing yourself?
Yeah, hi, I'm Katherine Powell. I'm also a water resource scientist with Linker, and I've worked with the Office of Water Prediction at the National Water Center for 3 years now. My training, I'm an eco-hydrologist. I'm also an associate scientist with the Field Museum in Chicago. For the National Water Center, I'm actually a technical director, and I work with the visualizations. So I'm going to be talking about how we get this all disseminated in mapping services.
All right, thank you very much, Katherine. So I'm going to go ahead and jump right into our presentation. Fernando has the first section here, so I'm going to turn it over to you.
Thanks, Carson. So as many of you probably already know, since there's some familiar names and faces in the crowd, the Office of Water Prediction has undertaken a significant effort in order to enhance the spatial and temporal coverage of stream flow forecasts in the United States. The legacy system, which was previously called the Advanced Hydrologic Prediction System, or AHAPS, essentially covered about 3,600 locations, most of which, or I think all, coincide with stream gauges. So it was a very, very sparse system. And now with the water model, we essentially have 2.8 million forecast points that span continental United States, Hawaii, and Puerto Rico. And then if you just hit the enter or next. So essentially the main output of hydrologic significance in the water model is essentially stream flow. And in order to essentially turn 2.8 million stream flow forecasts into flood inundation maps across the entire United States, some simplifying assumptions are made. So instead of using quasi 2D or 2D methods that can be very computationally expensive, especially at high resolutions, we essentially couple the water model with synthetic grading curves, which we'll get into in a second, and then terrain index known as height above nearest drainage in order to produce inundation extents and depths at 10-meter spatial resolution, hourly time steps, and multiple forecast horizons. Previously, the legacy forecasting system AHAPS produced flood inundation mapping products at about 200 of those 3,600 locations. So now we essentially have, a significant, larger footprint in terms of forecast flood inundation maps that are available in the United States. And again, I do want to clarify this is all basically in the fluvial context. We can go to the next slide. So I want to get into hand or height above nearest drainage conceptually. Basically what it is it's a detrending of a DEM. And what it does is it normalizes elevations away from height above mean sea level to height above unit relevant drainage line. In order to compute that relative elevation, you basically have to get your entire processing unit to drain. So all of your pixels have to monotonically decrease in elevations. You have to have hydrologically relevant flow directions. Everything has to drain into a stream network Thalweg pixel, and then your entire stream network has to monotonically decrease in elevations as well to an outlet point. So in order to do that, quite a bit of hydro conditioning operations have to take place. We won't get into a bunch of them, but you can imagine there's pit filling, there's levee enforcing, there's bathymetry adjustments, bathymetry burning, you name it. We're doing quite a bit of it in order to enforce this fundamental assumption of hand. So you can imagine that there are some limitations here that are being introduced into hand by fulfilling this assumption. But essentially, we mentioned that the water model produces reach scale discharges, and that is essentially how stages are developed. So we basically compute the Manning's equation, and Manning's equations are essentially typically cross-section based. We don't use cross-sectional geometric parameters. We use reach average parameters. So instead of like something, let's say like cross-sectional area, you're essentially taking a volume per stage slice and dividing that by the length of the reach. So you can see here, this is how you would essentially develop a synthetic rating curve. And then you would, essentially, once you built that relationship, you can use a national water model discharge to convert into stage. Next slide. And then you can hit next. So over the years, we have developed our own version of FIM hand-based FIM. And if you look back in the literature, if you were to go do some reading as to when hand started and the first national U.S. implementation, one of the first ones was called the National Flood Interoperability Experiment. This was a multi-agency, multi-institutional effort that occurred back in the 2015-16 time range. And essentially, we've, around 2019, we evaluated that compared to some engineering scale models. And you can see that some of the CSI scores for both 100 and 500 year synthetic events. And since developing our own version of hand, we've been able to make quite a bit of improvement. If you hit next. We've talked about some of these hydro conditioning methods. We've made some adjustments to Manning's ends. We use some new input data, and then we've been able to account for multiple fluvial sources. If you hit next. Some of these advancements and then some of the implemented details into what we do are available in this paper. It is under review. You can see here on archive. And then we do have all of our code is publicly available. We have essentially the way that you compute hand, the way that you produce FIM from the hand, and then also the way you would evaluate, the way we evaluate that FIM is also publicly available. So if you hit next. So hand has a fundamental limitation, and this slide essentially tries to convey what that limitation is and then our way around it. And what hand does is, we noted on the first conceptual slide, is it works on an independent catchment basis, meaning an inundated area can only have one contributing fluvial source, right? So that's it, just one, because it's on a per catchment basis. So if you look at the situation on the left here, this is an agreement map. So just a two-way contingency map, basically, for a hand-produced FIM compared to an engineering grade HECRAS model. So what we're seeing is you have a large flow, higher order main stem with 1900 CMS going through it. And then you have two tributaries flowing into it with much lower discharge or streamflow values going into them. Unfortunately, the high magnitude discharge going through the main stem cannot populate the regions that are draining into the tributary regions. So what that does is that leads to false negatives, the FN values symbolized in orange. So these are essentially regions of underprediction. If you look at the catchment lines that are labeled in white, you would actually just see basically a pool of water that is artificially filling this bucket beyond the height of the walls of the bucket, basically. So this is kind of like an artificial constraint that's being built up in hand. The way we solve that, you have to look off to the right. So if you look at figure A, basically you're seeing the hand-based flood inundation map used to create the agreement raster on the left. You can see the flow constricted areas circled in green. What we do is we discretize our stream network away from this very dense stream network of high stream order. We reduce it down to level paths, and you can kind of see the little GIF on the lower left that Carson made, that essentially discretizes your region into areas of singular unit stream order, basically. And then you compute hand on an independent basis for each individual level path. And what you see is, and you look at subfigure B, the same green regions, you can see that the water now expands to a much larger area. And it's because in the red lines, the catchments are now much bigger. You would compute that again for the level path in C, and then also for the level path in D. You would mosaic B, C, and D together, and it would look much better, which I'll show you on the next slide. I do want to call out before we move, we only produce these level path scale FIMs for stream orders 3 and above, because it's just really mostly relevant for higher flow tributaries and confluences. Next slide. So figure on the left shows a main stem, a very high flow main stem with a bunch of tributaries going into it. We boxed in these regions of false negatives. With the drainage order reduction technique applied, you could see that these regions essentially fill up with water now. So a good improvement in areas of high impact inundation is produced here. In addition to this, the team's been working on some other problems, one of which is obviously a lack of bathymetry representation that's available in some of the DEMs that we use. So we've been able to develop some techniques here that can estimate some of the missing bathymetry area. This method is known as BARC. It's bathymetry adjusted rating curves, essentially. And then additionally, roughness or Manning's end parameter that we use for our reach average synthetic rating curves. You know, that definitely has a flow stage dependence, right? So been able to threshold between in-channel and floodplain stages, and then we can vary Manning's end based on that. We've been able to find that that's also led to quite a bit of improvement, especially for lower flow events that tend to be over-predicted with the Manning's end that we use for higher flow events. Next slide. And then we've been able to advance some of the latest data sets. So just going to go over this quickly. Basically, the USGS has greatly enhanced the coverage of their collection efforts of quality level 2 data or above. Most of this is LIDAR, and it's rapidly approaching continental scale availability. And because it's approaching continental scale availability, we can now use it for continental scale applications. Previously, we did use the DEMs that were available in the NHD plus high res. Some of these were compiled with 3DEP data where available, but obviously they're dated, so they did not have this higher quality elevation information available at the time. So next slide. So we did a little comparison, and we compared 3DEP data resampled to the 10-meter resolution versus NHD plus high-res DEMs. And we resampled the metrics to the catchment scale. And you can see for the 100-year case, a pretty significant jump for all these 4 metrics that we're considering. And then you can hit for the next, the same, pretty much no statistical significance across the 2 magnitudes, but also for 500-year case, we're seeing quite a bit jump. So nothing surprising here. Higher quality terrain information leads to higher quality flood inundation maps. So next slide. All right, so you might be asking, oh, go back one. I'm sorry. Yeah, it's okay. So you might be asking, how do we evaluate these? Well, Unfortunately, flood inundation mapping, any benchmark data source is subject to uncertainty. There's a lot of uncertainty and errors in this field in general. So evaluation of continental scale inundation proxies is basically what HAND is you know, not a difficult problem, or it's a difficult problem. It's non-trivial. So what we've been able to do is one philosophy that we've adopted early on, and we're not tied to this philosophy, but it's the one that's been guiding us, is essentially decoupling from some of the hydroclimatic uncertainties that are presented inside of the National Water Model. And what we do is we use engineering scale models at a variety of scales. So either the REACH or REACHES scale, and then HUC 8 scale. And essentially we use the stage or the discharge values available from these models to produce the flood inundation maps from HAND. And then we compare those to the extents that are available from those models as well. So you can see here some of the sources, the AHAP sites themselves, which we're labeling here as the National Weather Service sites. We compare to those, the legacy sites. We compare to some USGS FIM sites that are available. We compare to FEMA, FEMA produced TECRAS 1D models for the base level engineering maps. And then Iowa Flood Center has been able to furnish statewide HECRAS models available at the HUC 8 scale. And we've been able to reproduce some of the evaluations in that region as well. So this is obviously not completely exhaustive list of some of the benchmark data sets that are out there. There's obviously room for remote sensing or high watermarks, but we just haven't gotten there yet. Next slide. And then this just kind of shows some of the spatial coverage of some of the evaluation sites. So we are trying to, you know, trying to distribute these as much as possible. There's obviously a lot of sparsity here. So we're definitely looking to increase the spatial coverage of our evaluation regions. Next slide. And with that being said, I will pass it along to Katherine, and she's going to go over into how these products are visualized.
Thanks, Fernando. Can everybody hear me okay?
Yeah.
I'm going to keep going. Yeah, as Fernando mentioned, basically, I'm going to review the National Water Center's visualization product, our decision support service. So right now, the National Water Center has a cloud-based hydrologic visualization and inundation services, or HydroVis system. This synthesizes the National Water Model output into basically a decision support services system, or a DSS system. It helps to answer, you know, crucial questions about events, in particular, you know, where, how bad will it be, you know, what the magnitude is, when will it occur, and some answers about probabilities as well. You can see here on this slide an example of two of those mapping services, the 10-day high flow magnitude and the 10-day high water arrival time. And the reason that we use these is because these aren't just visualized services. As I mentioned, they're a decision support service meant to be used in conjunction. Several services work together. Now, we have over 60 such mapping services currently, and they range anywhere from, you know, precipitation related to discharge or stream flow, and land surface processes like soil moisture or snow water equivalent. The FIM services fit into this by basically deriving the National Water Model stream flow or discharge into the inundation that Fernando discussed. So next slide. I'll tell you a little bit about how we deploy this, and then I'll go into a few more details about how we actually visualize those inundations. HydroVis services use the Amazon Web Service framework to create a data and processing pipeline that collects the output from the National Water Model and organizes it into a PostgreSQL relational database, from which we then post-process data and publish maps through an enterprise GIS platform. Right now, Esri is the one that we're using. Next slide. So the HydroViz set of flood inundation maps, including the forecast flood inundation mapping, basically are generated by using the local raster computations, the rasters and rating curves that Fernando mentioned earlier. And these are stored by the USGS hydrologic unit codes, or HUCs, specifically at the HUC 8 scale, again, as you might have noticed from Fernando's presentation. As you can see, there are over 2,000 HUC 8s in the continuous US. And this, coupled with the fact that they're roughly over 1,300 square miles each, it means that we're processing a lot of data in order to map these and visualize the rasters. For forecast FIM services, HydroViz processes roughly 3,000 HUCs per hour, or over 93,000 HUCs per day. Next slide. So just to give you an idea of how we do some of this, the HydroViz base FIM mapping services use the National Water Model discharge, and they use that value in order to find the hand FIM stage. And as, again, we mentioned before, this is through those rating curves, the synthetic rating curves provided by hand. These maps update regularly with the National Water Model runs, so hourly to multiple times a day, depending on what kind of output configuration. That would be from the analysis, the short range, and the medium range. Since the National Water Model generates output for about 2.8 million reaches, this is a lot of data, obviously. And the services, in particular the FIM services, then we filter this discharge value before we do any of this mapping. And I'll talk about this in the next slide, but we basically use discharge that is equal to or higher than an OWP designated high water threshold. And then as I mentioned, because of the volume of data, this actually makes this process far more efficient. Next slide. So I'm going to quickly summarize the high water threshold that I mentioned. The OWP designated a high water threshold basically as an indicator of elevated flows that the operations division uses to focus on areas that have flows that consider to be significant enough to monitor. In order to derive this high water threshold, as you can see from the image here on the left, we conducted some flood frequency analyses using the 40-year National Water Model 2.1 version reanalysis. The resulting stream flow annual exceedance probabilities, or AEPs, are used in a lot of our services, but in particular, we use some of those lowest return periods to determine where we want to start looking at monitoring flow. So I'll mention also how some of these other APs fit into some other of our services, but for now, focusing on the high water threshold, we used these streamflow AEPs and evaluated them against categorical National Weather Service action stages, other stages actually, but specifically the action stage. Now you can see from the image here on the right, what we are doing is comparing 4 specific regions. We have 11 regions that we divided it up into. We compared the median action with the median of a 1.5 return interval calculated for the National Water Model. And essentially, we just adjusted those until we came up with a good representative high water flow per region. So for example, if a region has a high flow threshold set to a 2.1 return period, then all the reaches within that region will use the discharge that's related to that reach's 2.1 year return period as the high water threshold. Next slide. So there are several other types of hydrovis FIM services that aren't the forecast FIM or the regularly updating one. As the previous slide mentioned, we actually utilize those other calculations for streamflow AEP. So the hydrovis AEP FIM that you're seeing an example of here actually shows inundation extents at every reach for various streamflow AEPs. We basically go all the way up to 2% or 50-year return period. These are actually not regularly published, but it's not technically a static service. We'll update it every time we recalculate these AEPs, but it's essentially a pretty static service right now. Next slide. Okay. Currently, the hydrovis regularly updating FIM services actually include a QC FIM layers. I'm not really sure this was the image I was going to use, but I'll just talk about this anyway. So, Carson, do you mind going to the next slide, see if it has another?
Yeah, I think it's progressed.
And one more. Yeah, this one. Let's stay here on this one. Actually, you can go back and I'll end here. How's that? And so, as I mentioned, a lot of our regularly updating FIM services actually have what are known as these QC FIM layers. And the FIMPACT group of layers actually uses this estimated impacted buildings layer. You're looking at one of the prototypes for that as we move through these, and then we'll end on the more close-up version. Obviously, what you're looking at is zoomed out, the hotspots that help you to zoom in on the actual layer that shows you the building impact. So in this last slide, the building footprints basically show the intersection with the National Water Model FIM inundation. The source of the building data is the FEMA USA structures database. Now, there's also in some areas some occupancy type data, but obviously that's limited by where it is available. It's still quite a few places though. The FIMPACT services, while we're showing you this estimated impacted buildings, we're calling them FIMPACT because we're actually developing more. We're going to augment this particular layer with even more services that are useful in the same way. And next slide. And, we actually do have to mask some of the inundations. Usually this is just in a few select areas where we know that the discharge or the flow is not well characterized by the National Water Model, or where inundation is likely just inaccurate for a variety of reasons. What you're looking at is one example of that. Currently, we mask levee protected areas, and we get those from the ones that are identified by the U.S. Army Corps of Engineers. Next slide. A lot of the services through hydrovis are already public, but not flood inundation mapping currently. However, hydrovis prototype FIM map services will be released to the public, and that is for their review. Hopefully, we're targeting sometime at the end of this year. The rollout will proceed in a geographically limited way, though. You're looking at the two areas that we're going to focus on here in those red polygons. Well, starting with 10% of the continuous US, and that would include areas in East Texas or the Gulf Coast and the Mid-Atlantic. Both of these regions have been working with OWP extensively for years now, particularly on our mapping services. Development of HydroViz decision support services continues. We're adding more maps, in particular, the FIM is very crucial to this. And we will be adding more even before we roll this out to the public at the end of this year. So to discuss the FIM development projects that are going on and our future direction, I'll hand you back to Carson.
Cool, thanks, Katherine. So yeah, Fernando kind of went over the current science and workflow that we use to develop FIM, as well as the different techniques we use to evaluate FIM. And Katherine went over more of how we use the outputs of that hand model to produce actual inundation for these real-time services. And so I'm going to go into a little bit more of our current and future development projects, including inland and coastal flood inundation. So Hydrobug Nearest Drainage or HAND is a great model. It's very cheap computationally. You can run it anywhere that you have a digital elevation model with B and a stream network to identify those the thaw entrances in order to produce the hydrodynamic drainage. But it's not really the most accurate hydrodynamic modeling models that's out there. So there's a lot more. There's a lot better sources of hydrologic modeling that's available, including HECRAS. We have 1D and 2D HECRAS modeling that was done for the FEMA base level engineering or BLE maps. We've also got the flood models and then the new calibrated 2D HECRAS models that are starting to be rolled out. But as we go up in this figure, there's an increasing cost, both computationally and storage-wise, and also data-wise. So wherever there's we can't just pop up a new HECRAS model where you have to go out, survey, and do all of the off-ground work. So what we're working on doing, we're working on taking these higher fidelity models where they're available and adapting them to our FIM workflow so that we can get these better predictions, better hydrodynamic model predictions where they exist. One of the things that we have experimented with is the list flood FP model. And the goal of this was kind of to use list flood FP to produce a library of maps. It actually worked out pretty good, but it didn't really scale very well. So we have temporarily shelved this project in favor of using HECRAS directly. So what we're working on right now is to use HECRAS, and we developed this software. It's open source on GitHub. It's called RAS2FIM. And what RAS2FIM does is you can take any 1D HECRAS model and turn it into a flood map. And so what we're doing is we're running several different flows through this HECRAS model and producing a FIM libraries with a synthetic grading curve similar to how HAND has a synthetic grading curve. And operationally, what we'll do is we'll use these pre-computed libraries to grab the right flood extent for a given flow, either from the national water model or from the river. So yeah, this is kind of what that looks like, using these pre-computed libraries to pick out the right extent. This slide shows the Army Corps of Engineers HECRAS model coverage. We're currently ingesting these models and running FIM on them so that we can produce these FIM libraries where they're available to use operationally. Then the next slide has, oh yeah, so this shows we're focusing on the 10% area that Katherine was talking about earlier, that first public 10% area. And this shows the FEMA PLE HECRAS model coverage that we're also ingesting using that FIM workflow to produce flood records. Okay, so besides inland flooding, we're also working on coastal flooding. So the National Water Model team is working on this total water level modeling. And what this does is it uses the SCISM model. SCISM is a semi-implicit cross-scale hydroscience integrated system model. So what that does is it uses P-surge and SPA on the ocean side it's a finite element model to produce the boundary conditions for that finite element model. And then on the inland side, it uses the National Water Model and river forecast center forecast to produce a mesh grid, and then we use that grid to interpolate the water surface elevation map or raster. So what we end up with is, okay, so this is the total water level domain here. So pretty much all of the coastal US domain, except for Alaska. We will be expanding into Alaska later this year though. So what we end up with there is some coastal inundation. So these are some of our first past experiments using some historical data from hurricanes. So you can see we've got Hurricane Laura up there, top left, Hurricane Harvey, as well as Hurricane Maria on the right there around Puerto Rico. So we have now the ability to use the tides and storm surge models to help us predict inundation around the coast. So now that we have all these different data sources, the challenge is going to be how are we going to combine them together to give NOAA and to give the public the best or even one fully integrated flood inundation map product. And so to do that, we in the coastal areas for the coastal domain, we will use the total water level FIM or the SCISM model, which is what's running under the hood on that, to produce FIM maps around the coast. And then where we might have a inland hydrologic model output like HECRAS or maybe list flood or some other model that we might look into experimenting with. We'll use that inland model where we have that data available, and then we will use hand to fill in the gaps everywhere else. And that's really what we have for you guys today. So yeah, we can take questions at this point.
Any questions from here or online? You can unmute yourself if you have a question online.
Are you interested in getting more data points in some of these places to be able to enhance the modeling?
So data points as in high water marks or
yeah, something like that.
So yeah, that's another one of the things that we're looking into high water marks, both to evaluate our data performance and also use high water mark to calibrate versus grading curves in hand. So yeah, that's another area that we're pushing into right now. But yeah, we are looking for any opportunity that we can to ingest any data that we can to improve our mapping.
And how about the use of all these models into flash flood? Because we have policies supporting that now, right?
So right now, we're only dealing with fluvial flooding. So we don't do any fluvial or flash flood based inundation.
But is that of interest?
It is of interest.
Okay.
Good. Yeah, so like on that first thing, we're doing this kind of generalization, and it seems a lot quicker. Is the validation of those models based upon historical, actual on-the-ground data, or is it based on how it compares to more computationally intensive processes?
Yeah, so right now we're just doing model comparisons using the FEMA BLE models and the FIM AHAPS libraries. So it's these agreement maps, they're produced from those model comparisons. So currently we are not doing any comparisons to like observed on the ground, like using remote sense data. But it is something that we are interested in. There are some issues with remotely sensed data, clouds, vegetation, of course, but also like if the image is captured right at the top of the hydrograph, then you might get some ponding involved if you're on the falling limit of the hydrograph. So that can compound some results maybe. And there's also the issue of getting a discharge for the time that the photo was taken. Hopefully there's a gauge nearby that we can pull some flow values from. But yeah, it's definitely something that we're wanting to fix.
So thanks for the very good presentation. It was very informative. My question is about toward the last portion of the presentation, which is about talking about your distinguishing, separating the sections into coastal versus riverine versus and using schism for the coast and hagras for the. So what is the criteria to distinguish between these and to recognize that up to this point would be like coastal, and then beyond that it's gonna be riverine?
Yeah, so right now we're using the 10-meter elevation mark. So everything below 10 meters above sea level is going to be done by the total water level which is given. And then everything above 10 meters is going to be inland and for the hydrograph.
And a second, though, very quick question is that the schism is becoming integrated into these flood inundation mappings that prior to that ATSIC was promoting a lot. And so have you had any difficulty dealing with the stakeholders and end users who are relying on using the products, or is I'm assuming that once you had from HIPRAS 1D to 2D the policies and like transferring all those and then moving between models, how these will be handled through this process? Because they've been already community built around ATSIC, and now schism is all. Technically, we know that there are advances, but can you share some experiences with that?
Yeah, I mean, that's a really good point. We want to make sure that the services we're using or that we're producing, we want to make sure that people are going to use it. And so it is kind of an ongoing thing since we're still building, still researching. We are in constant contact with internally with our field folks, so the people at the weather forecasting offices and river forecasting centers who are actually putting out some of these discharge forecasts. We're making sure that they are looking at these services and that they are actually using And then we're also in contact with, on the coastal side, with the National Hurricane Center within NOAA to make sure that everything we're doing, they're aware of. And as far as outside stakeholders, we are also working with, you know, of course, Cairo, but also we're working with big time partner with UT Austin, who's actually running PAN for the state of Texas. We're doing it at the 10 meter scale right now, and they're running it at the 3 meter scale. They've got some 3 meter resolution battling data during the state of Texas. So we're working with them, who also partners with Texas DOT to make sure that we're producing a viable product that's going to. Does that kind of answer your question? I mean, so you did mention, sorry, the HEC-RAS like 1D, 2D stuff. So right now, FIM only does 1D models. So one great thing that we would like to do is, since 2D is becoming more and more common, is to upgrade FIM so that they can use that 2D HEC-RAS. But currently, it only uses one.
So Fernando explained that you decouple the development of your hand FIM from the national water model, so it doesn't, introduce those biases from the model. So maybe, I don't know if Katherine is the address for this, but have you done some analysis, or do you have a sense of how much of the bias in your FIM forecasting is due to the national water model biases and errors?
I think I heard, did you want me to jump in here? I think I heard.
Yeah, sure.
Yeah, okay. Yeah, we do have an entire group that does nothing but do evaluations on not just the visualizations that we put out there, but some of the national water model. And we're just starting the process of trying to figure out how to incorporate those into some of the information that you're getting, specifically like in those QC FIM layers. But I would say it's a work in progress right now. And it's also not something that we would necessarily want to create a visualization for. It could be something that we're doing offline. So even if we don't have necessarily a mapping service that specifically addresses that, it doesn't mean that we don't have the information in-house at National Water Center. I hope that answered it.
Yeah, I'm just curious. This is just purely curiosity. If we know, if you have even a more just general sense of, is a lot of the bias in the flood inundation mapping due to just problem with hand or whatever model, or is it associated with the national water model discharge predictions? Again, I don't know if anyone has that answer.
My sense is that, yeah, there are some known areas, and operations actually has sort of a internal knowledge and documentation they use to know exactly where the national water model is having more challenges in doing forecasts. Now, these are also time dependent because it's not just a matter of spatially. There are definitely challenging areas, there are challenging times. So where the national water model might do really well in certain regions, I'm thinking of the Southwest, it could do a great job all the way up until they have sort of a substantial, this is just an example, I don't know specifics, but right up until they have a big flash flooding event, for example, and that is when, some of the discharge values from the national water model will definitely bias, and we don't get great FIM. One of the things I forgot to address too is within the operations division, they actually are collecting, it's still qualitative at this point, but they do event reviews, and during events, they're actually reviewing our FIM compared to other data that's available. And so we're getting a lot of feedback about where it's doing well and where it isn't.
I would just follow this comment with, I think that's probably an argument for this uncertainty about whether there, the errors in the model versus the error in the hand versus the errors is actually something you can take and say, yeah, this is actually an argument for the kinds of comparisons you're doing, which is a high resolution calibrated 2D model against a hand or a hand plus or hand plus plus or a fist or whatever it's going to be. And so because you're saying at this flow rate, what do we get with 2D modeling? And what do we get with, regardless of whether or not the flow rate is correct, it's just comparing at those flow rates, what would be the most correct or good representation. So I think there's so much error in the national water model itself still that those kind of comparisons probably make more sense that you guys are currently doing.
Yeah, and I also will add to that and say that we are producing, there's several different configurations of FIM, but one of them is called RFC FIM or river forecasting. That's where we take the actual discharges that are forecast from our river forecasting centers, so humans running the CHIPS model and analyzing the output and saying, okay, I think it's going to be a discharge at this forecast location, the AHAPS location, is going to be 30,000 CFS. We ingest those and then produce FIM using those RFC forecasts. And we route it downstream it uses the same routing algorithm that the National Water Model does, but instead of using the rainfall runoff model like the National Water Model does, it kind of puts the forecasting into the RFCs.
Yeah, you just need a flow number.
Exactly. Yeah, we just need a flow,
and then you can flood whatever.
So what we found with both our operations division at the National Water Center and also at the RFCs and WFOs is that they really like that RFC bin because they can control it, right? They can control the discharge, and they're not fully reliant on the uncertainty associated with rainfall forecasts. We use GFS for our forecast right now for the medium range or uncertainty that's associated with the rainfall runoff water model. So we're trying to take as many approaches to this to give our forecasters and eventually the public ability to make decisions.
See, if you just wanted a flow, can't you actually just disconnect these two problems? Like you do your own flood inundation separately, create a big some sort of a lookup table, and they do their job and then simply just call that and do it, basically. Why do they have to be coupled? And
that's a really good point. So that's exactly what this AEP FIM service is kind of doing. So we're taking, it's based on the National Water Model retrospective analysis, but it's just taking that flow, running it through hand, and saying if you get this amount of flow, we also produce for the attributes feed, we have the actual flow values in CFS that you can look at. So saying, okay, with 30,000 CFS, this is the area that's going to be. So that's what we're trying to exactly.
Because that way it would be a one-time deal in a way, right? I mean, to follow up Sagi's question, you can completely dislink these two problems, and you guys do everything to the best of your knowledge, given a flow with DM and all the elevation information done, put it in a big table, and literally you're done, actually. Then leave it to the National Water Model to get the flow. If they get the flow right, you get the inundation right. If not, it's not.
I think there's a problem a little bit with that because one of the issues that I've been following is kind of like about the eternal fires that's basically coming from caves that are set on fire and there's no way to turning it off. So the flood model, if it doesn't account for spaces on Earth like that are caves, and so the water can go in then I can see that some of these discrepancies, if you don't have ground monitoring, to collect the data, then you're not going to be accurate because you're basically just assuming that either the ground is in a sponge or that is flat and is going to run. But what about all these other holes that exist and can actually take in the water?
Yeah, so that's what the National Water Model attempts to do. Is it has a groundwater portion to it where it tries to model how much of looks at the soil, it looks at the groundwater, depth of bedrock, all this stuff, and tries to predict how much is going to be added to the groundwater versus how much runs off into the stream. Now, obviously, there's going to be a lot of challenges associated with like Carson topography, like you're saying, caves, but that's one of the challenges.
Yeah. And I can see that could create a lot of issues, principally like here, Alabama, Florida, because if you look at the amount of sinkholes we have is something phenomenal, right?
All right, we're at the 1 o'clock. I'm happy for anyone who wants to stay and stay behind. If Carson and Katherine want to stick around and chat, I'm definitely for that, but I don't want to hold anyone that needs to go and just waiting patiently. So it is well online. So if there's more food left, please take some more, right? We don't want to do that. Thank you. Thank you. Oh, tomorrow. I can show you what we know.